So the step 3 is determining of our test statistic. Okay. Now, depending on what test you are conducting, if the claim was on, the manufacturer said the average, okay, claims that, so let me say the test, okay, or what the claim is about, and then the type of test statistic you employ. Okay, so the test statistic we're going to employ. So test statistic we employ. Now, if the manufacturer is making a claim about the average lifespan, like we just see, average is what? Is mu. Okay, so if the person is talking about average, then there can be two types of test statistic which we can employ. The first one will be the set statistic, which we have already seen. That's the Z-score, which we've seen. Or we can have the student T statistic value. Okay, very good. Then if the person is also making a claim about proportion, so for example, somebody says that I'm going to, maybe a political party says, I'm going to make 50 plus 1 or 51% of votes in the coming election. Okay, that is a claim which you have to test. So when you go out there, you go and select, okay, people from various communities to test whether the claim is true or false. Now, there are ways also to go about that. Okay, so we can test the claim of the proportion using what? Either a binomial, okay, test, or we can also use the Z test for that. Then we can also test for variation. Somebody says there is a difference between this and that. Okay, we want to find a difference. So if the difference between maybe drug type A or fertilizer A and fertilizer B produce different yields. So if you want to test for differences, which will be mean 1 minus what? Mean 2. Okay, that 2 we can use what? Z, or we can use what? T. Then if we want to test for variations, okay, we want to test for variation. So if the test is on variance or on the standard deviation, then there are a number of tests we can conduct. We can have chi-squared. We can have the F statistic, okay, when the populations are more than what? 2. Okay, so there are a number of test statistics which can be employed for various what? Type of test, okay? But in our class, we are going to focus on what? Test on the average. And then time allowing us, we also look at the test on what? On proportion. Those will be the two key things we'll look at in what? In class, how to go about it. So the next thing we are coming to look at is the test on a single population what? Mean, okay, which is for this claim. Okay. So like we said, in testing for a single population mean, all we need to do is to use the Z statistic, okay? And using the Z statistic too, we know that the Z statistic is always what? It's always giving us what? Don't forget, everything we are doing is using samples. So we are talking about the observed sample mean minus the claim value, which is mu, over, we have the population standard deviation over square root of n. I think we've seen this already. Very good. Yes, however, in reality, most of the times we we do not have information apart from the claim. As for the claim, the manufacturer will give you the information. Okay, yes, but the standard deviation might not be given, okay, by the manufacturer. You understand? So if it's not given, then there are two cases. When the standard deviation is, or the variance, either variance or standard deviation, is unknown. When it's not given, when we say it's unknown, we mean it's not given. You do not know it from the question. It's not given or it's not provided. Okay, good. So when it is not known, then there are two scenarios, okay, you need to consider. One, if the sample size is greater than or equal to 25, okay, yes, then what you do is you will still use the Z statistic, okay, and then you have to replace, because your standard deviation is not known, you replace the standard deviation of the population with the sample standard deviation, which is S, okay, over the square root of N. You remember in the beginning slide, we said that in the beginning we said that S squared is an estimator of what? Your population variance. So the same way, the sample standard deviation is an estimator of the sample variance. Yeah, so in the event where you don't have the variance or the standard deviation from the population, from the manufacturer, or from whatever test you've been asked to conduct, then you make use of what? The sample standard deviation. But if your sample size N is less than 25, then you will have to use what we call as the student T distribution. But it's the same approximation. The only difference is how the T value will be read. It will be read from a student T distribution or table, but it's the same formula though. So you calculate your T value, which is also S over square root of N. But when you are reading your decision rule, okay, you are going to use T of alpha or T of alpha over 2, and then we have what? N minus 1 degrees of what? Of freedom. That is if it is one tail. Okay, so we'll be looking at those details. Well, let me state all two conditions. So if it's one tail, we'll be looking at T of alpha N minus 1, and then if it is two tail, we are looking at 2 of alpha over 2, alpha over 2, N minus 1 degrees of freedom. Okay, and then for the Z scenario, we'll be reading Z's, okay, of alpha, okay, as a critical value, okay, and then Z, we'll be finding the critical value of Z of alpha on 2 for a two-tail what? For a two-tail test. Okay, so these are the conditions associated with the testing. So what we are saying that ideally, this is the test statistic. Okay, ideally, this is the test statistic. But because we usually don't know the standard deviation from the manufacturer or from the population, you have to check if your sample size is large or small. If the sample size is 25 and above, which we say is large, okay, then we use the set, we still approximate, because the central limit theorem says that as your sample size gets large, okay, your distribution becomes more approximates a normal process, okay? Good. So we can approximate it to a normal distribution. Whilst when n is less than 25, we make use of the t distribution. Well, there has been some ongoing debate, okay, for sample size of n equals to 25 to 30, okay. Some are of the view you make use of the t distribution and then use a correction factor, okay, there. Others are of the view you just make use of n greater than or equal to what, 25, and that is what I've provided for you in class. Okay, any question? Any question? If you don't have any question, please write what you see on the slide there. Okay, and then let's solve an example. Write exactly what you are seeing projected up here. And let's take an example. So I've given you some 2 minutes to do that. Then we take the sample. Okay, I'm sure you are done with what I asked you to write. So let's take our example now. So I'm clearing the screen. Yeah. So I'm clearing the screen. Yeah, so let's take an example. Yeah, I think I've explained it. So let me just. Okay, so Salim, you're asking me to go back to this one. So what I'm saying is anytime in very short, okay, form, what we are saying basically is in an example, when you notice your sample size is greater than or equals to 25, you use the set statistic, okay, good. If your sample size is less than 25, use the t statistic, okay. The formulas are the same. The only difference is how you are going to reach, okay, the critical values from the statistical tables, okay. For this one, you read from standard normal table. This one you read from student T distribution. So basically, that is it for all the things that I said. Then again, depending on the statements of the alternate hypothesis, okay, yeah, we can have what we call as one-tailed test and two-tailed tests. So for one-tailed test, we can have two types, okay? If the statement says we are looking for mean less than a certain mu value, okay, then what we are saying is, then the rejection will be on the left, because less than obviously means we are reading from the left to some point on the left. Okay, good. Then if it is greater than, like we've been doing all this work, if the value is rather greater than means you have your points. Let me redraw this. So you have the normal distribution. Then you have point greater than on the right side. So less than is to the left, greater than means on the right. Okay, so the rejection will rather be on the right. Okay, so we say for the left scenario, we say one tail, one tail but left, and the rejection is on the left. For the greater than, we have one tail on the right, rejection is on the right. Then for a two tail, okay, two tail is when we have not equal to. When somebody says not equal to means it is either less than or what? Greater than, okay? So when you say not equal to, then you are saying that mu is either less than mu naught or mu is greater than mu naught. So we have two scenarios. Not equal to can mean it is either less than or greater than. So we can have these two scenarios here. So that will give us what? Less than. The less than portion will be on the left, and then the greater than portion will be on the right. Now the issue here is because the rejection has been divided into two, okay, the alpha, you remember we said the significance level alpha is the maximum of total probability of what? Of rejection, okay, in very simple terms. So if for a left tail test, this is alpha. This is the total probability, alpha. For a right tail test, this is going to be what? Alpha. Okay. But for a two tail test, alpha has been splitted into two equal parts. So this portion is going to be what? Alpha divided by what? 2. And then this will also be what? Alpha divided by what? 2. So that when we add the 2, we get the maximum probability of rejection, which is alpha. Alpha over 2 plus alpha over 2 will be what? Alpha. So anytime you are conducting a two-tailed test, anytime your alternate hypothesis, okay, has the mathematical form of mean is not equal to some value or a claim value of mu, then you are going to use what? An alpha of alpha over 2, okay, in your estimations. Now let's move on to demonstrate whatever we have done with an example. Yeah, so we are giving an example here. Let me clean this one. Yes, so we've been given an example. It says that a random sample of iron rods showed an average length of, what is that? Torque. So time for this. So a random sample of 1,000 iron rods recorded showed an average length of 71.8 centimeters. Okay, so don't forget this thing we are saying random sample, random sample. So that is your sample. Do you understand? So the 71.8 you are seeing here is what? Your sample mean, which is X bar. Do you get it? So your random sample of 1,000. So your sample size was 1,000 iron rods. Okay. And then your sample mean is what? 71.8 centimeters. Then we are being told, assuming the population standard deviation. So here in the question, you've been told or you've been provided with the population standard deviation. So assuming the population standard deviation, which is sigma, is what? Is 8.9 centimeters. Okay. Then here comes the investigation. He says, does this seem to indicate that the mean length of all iron rods is greater than what? 70 centimeters. Okay. So he says that this indicates that the mean length of iron rods probably produced by some company, okay, is greater than what? 70 centimeters. So this is the claim, the test you want, the investigation you want to what? Test as to whether the average length of hello, Eugene. So Eugene, kindly make me the host. Okay, thank you. Yeah, so let's continue. So like we said, because, okay, we are interested in testing whether the mean length of iron rods is now greater than what? 70 centimeters. You write the statement that mean is what? Greater than what? 70 centimeters. Okay, good. That is what we've been asked to investigate. Okay, does this seem to indicate that the mean length of rods is greater than 70 centimeters? So this is what we are investigating. Then the opposite statement, yes, Dennis. Dennis, I've unmuted you.
So you proceed. I'll ask you later.
Okay. So the investigation here is to check if the mean length is greater than what? 70 centimeters. So you're right. Mean is greater than 70 centimeters. Then step 2 is to write the contrary, because it's an experiment. You see, it's either going to be true or false. So the contrary statement will be less than or equal to 70 centimeters. Then final step is to identify which one is more. Small always has an equal to. So this becomes the null hypothesis. And then this becomes the alternate hypothesis. Okay, very good. So like we said, anytime we are testing, okay, we test the null hypothesis. In hypothesis testing, we always test what? The null hypothesis. Okay, good. Now, and then anytime we are checking for the critical value, we use the notation on the alternate hypothesis. Okay, very good. Very good. So let's continue. Now, we were told to use alpha of what? 0.05, which means alpha of 5%. Okay, 5%. So that is stated in the question. So step one, you have indicated what? Your null and your alternate hypothesis. Step two, you've indicated your alpha length. Step three, we are supposed to determine whether that Z or T in using Z of T, first you have to check whether sigma is given. Okay. You remember we said if sigma is given, you just use it. But when it is not given in the question, that is when you look at the size, whether it is large or small. But we are fortunate here. We're given, we said, assuming the population standard deviation. Okay. So the population standard deviation of sigma is given in the question as what? 8.9 is be stated in the question, 8.9 centimeters. Okay. So once it's stated, you don't even ask yourself whether sample size is small or large for you to check whether you are using Z or T. Once it's given, you are going to make use of what? Z. So we have the Z statistic here. Okay. It's the same thing you were seeing earlier. X bar minus what? Mu over what? Over sigma, the standard deviation over the square root of what? N is the same thing. Okay. That is the Z statistic. So we've been told that our random sample N was 1,000. N was 1,000. And then the X bar for the sample was what? Was 71.8 centimeters. Okay, so it means we have all the values, okay, at hand. X bar is known, the X bar here is known. The mu is the claim value, which is 70. That too is known. The standard deviation too has been provided. And then the sample size too has been provided. So we are just going to put them into the formula. So sample mean is what? 71.8. Put it in the formula. Then the claim value, we're supposed to test if it is more than 70 centimeters. This is it. Then the standard deviation too has given here. Okay, so you put it in. That's 8.9. And then divided by the square root of n. N2 has divided as 1,000. So you put it there. Okay, and then you do the calculation. So you calculate it from your end. First, find the denominator, okay, which will be square root of 1,000. 8.9 divided by square root of 1,000. So find that for me. So 8.9 divided by square root of 1,000. Okay, So then you find the numerator to and divide by the denominator. So Salim says 0.2814. So basically this is supposed to be, let me just do this for you. So if you look here, this is what Salim is saying. This gives us what? 1.8 over 0.2. Let me check again. 0.2814. Okay, 0.2814. Okay, so when you calculate that, that should give us 1.8 divided by your answer gives us what? Yeah, so we are getting 6.3956. 6.3956. Okay. Okay. So having obtained this, I'm sure some of you are still doing the calculation. So let me be a bit slow. Yeah, so after you've obtained step 4, I'm just giving you some time to wrap up your calculation. Yeah, so you can leave it in 4 decimal places. Okay. Yeah, so once we've reached here, okay, we need to do step. So what you realize that in step 4, we've actually brought step 5, okay, all the way to step 3. We're actually doing step 3 and step 5 together. The steps you wrote. So we want to go and formulate the decision rule, which is step 4. Okay, good. Now, there are 2 ways to do that. Okay, one way is to, let me clear the screen first. One approach is to estimate the p-value. Okay, we estimate the p-value and compare with your alpha value to decide. Okay, we're not going to use that approach for now. Okay, good. We'll look at that later when we get to class. Then the next approach is to use what we call as a critical value. So the critical value, you remember earlier, okay, I indicated that we have a rejection region. You have an acceptance region and a rejection region. So if this is your acceptance, okay, you have rejection, you will have rejection here. Okay, now these values, okay, we call them the critical limits. Okay, the critical limits. Or yeah, the critical limit. Okay, so you find the value of that critical point, okay, which forms a critical limit. When we say critical limit, we just mean that point which separates acceptance from what? From rejection. Okay, that is what we mean. The point which will separate your acceptance from rejection. Good. So let's go back to what we are doing. Now, we have to revisit, we formulate our decision rule. You need to revisit your alternate hypothesis. In the alternate hypothesis, we were told that mu is greater than what? 70 centimeters, okay? Greater than means we are looking at a rejection on the right, if you recall, okay? So when we say greater than, then we are looking at the rejection, one tail test, but the rejection is on the right, okay? So let's just cast our minds back a bit. So when we have mu is greater than mu naught, then we are saying one tail test with rejection where on the right. That's the second scenario. Okay, so let's go back. So it means that our rejection is going to be on the right, like we are seeing in this graph here. Okay, now the next point, the next thing to do is to find what we call as the critical value. Okay, Z critical. So the question is, how do I get the Z critical value? Okay, good. You make use of the alpha value given. Alpha was given as Z critical value is always given for a one tail test is given by Z, okay, with probability of what? 0.